You just had a brand new idea for an awesome project. You believe that the idea for this project is going to take the world by storm. Users and developers alike are not prepared for the next big thing in tech. So you open up your favorite editor, and I'm guessing it's VS Code. Except, of course, you're already on the Vibe train and you're using one of those overhyped VS Code AI Fox, which is still VS Code, by the way, just with a lot of AI packed into it. Let's assume you decide to use a modern programming language like JavaScript or Go, and you go about building your awesome new project you are probably going to abandon in the next 2 weeks when you get another new awesome idea. You create variables, arrays, and objects, making sure to suck every available memory from your PC. Your program works or barely works. You don't know how or why it works, but you do know that it works, and that's all you care about. But let's pause for a moment and ask ourselves, how come I am not using up all the available memory in my CPU despite creating so many variables and objects? Somehow, it seems that your app runs smoothly with little to no performance overhead. You ask yourself again, how come the objects in my code are not using up all their available memory? Well, this is because of the very awesome garbage collector that sits at the heart of your favorite modern programming language. And this is going to be our focus for today's video. We are going to take a look at garbage collection, what it is, how it works from top to bottom, and why it is so useful and found in almost all modern programming language. If you think that's a great idea, then absolutely smash the like button. Ensure you subscribe to the channel to get access to all of our videos in the future as they drop. Make sure to stick around to the end because I have a challenging question for you. Let's start with garbage collection. What the hell is garbage collection? Garbage collection is a form of automatic memory management that involves automatically reclaiming memory in a computer program that is no longer being used. It frees the developer from manually tracking and releasing memory, reducing the risk of memory leaks. The garbage collector attempts to reclaim memory that was allocated by the program but is no longer referenced. Such memory is termed garbage. Garbage collection was invented by an American computer scientist, John McCarthy, around 1959 to simplify manual memory management with Lisp. Before the introduction of the garbage collector, a developer was tasked with hunting down objects that have gone out of scope in the program and deallocating that object from memory like a caveman. Garbage collection is not all sweet and no sour, as it may take a significant proportion of a program's total processing time, and it affects the performance of that program as a result. We have already established that most modern programming languages incorporate a garbage collector either as part of the language specification or effectively for practical implementation, and these are known as garbage collected languages. Examples are Java, C#, Go, and JavaScript. Languages such as C and C++ were designed for use with manual memory management. Some languages like Ada, Modular 3, and C++ allows both garbage collected and manual memory management to coexist in the same application by using separate heaps for collected and manually managed objects. Let's look at some garbage collection strategies. We talk about two major types of garbage collection strategies, namely the tracing garbage collector and the reference garbage collector, starting with the tracing garbage collector. Tracing garbage collection is the foundation of modern JavaScript garbage collectors. It is a strategy that identifies and reclaims memory by determining which objects are still reachable from known root references. This is the most common type of garbage collection, so much that the term garbage collection often refers to the tracing method. Tracing collectors are called so because they trace through the working set of memory. The garbage collectors perform in cycles, and it is common for cycles to be triggered when there is not enough free memory for the memory manager to satisfy an allocation request. When talking about tracing garbage collectors, we need to talk about reachability. Reachability determines which objects stay in memory and which gets garbage collected. An object is reachable if it is referenced by at least one variable in the program, either directly or through references from other reachable objects. Objects can only be reachable in only two ways: global variables and objects that are referenced from anywhere in the core stack, that is, all local variables and parameters in functions currently being invoked are reachable, while anything referenced from a reachable object is itself reachable. Let's look at some algorithms that are using the tracing garbage collectors, starting with the mark and sweep garbage collector. The mark and sweep algorithm is the core algorithm behind JavaScript's garbage collection. In the naive mark and sweep method, each object in memory has a flag, typically a single bit which is reserved for garbage collection use only. Let's look at the phase 1, which is the marking phase, where we identify reachable objects in the mark and sweep algorithm. A tree traversal of the entire root set is carried out, and each object that is pointed to by a root object is marked as being in use. All objects that those objects point to and so on are also marked as being in use, so that every object that is reachable via the root set is always marked. Let's look at phase 2, which is the sweeping phase or the memory reclamation phase of the mark and sweep strategy. In the second stage, all memory is scanned from start to finish, examining all free or used memory blocks. Those that are marked as not being in use are not reachable by any route and their memory is free. For objects which are marked as in use, the in use flag is cleared so the garbage collector can prepare for the next cycle. This method has several disadvantages, the most notable being that the entire system must be suspended during collection and no mutation of the working set can be allowed. This can cause programs to freeze unpredictably, making some real-time and time-critical applications impossible to build with such systems. And this naturally leads us to tricolor marking. Tricolor marking is a specific technique used within the mark phase of the mark and sweep algorithm. It categorizes objects into 3 distinct colors. Because of the performance problems associated with a naive mark and sweep garbage collector, most modern tracing garbage collectors implement some form of variant of the tricolor marking abstraction. 3 sets are created: white sets, black sets, and the gray set. The white set or contempt set is a set of objects that are no longer being used and they require cleanup, while the gray set contains objects that have been discovered but their child references have not been fully scanned yet. The black set is the set of objects that have been visited and all of their children or references have also been visited, so they are confirmed as live. In many algorithms, initially the black set starts at empty, the gray set is the set of objects which are directly referenced from roots, and the white set includes all other objects. Each object in memory is at all times in exactly one of 3 sets. The algorithm proceeds as following. First, you pick an object O from the gray set. Then, you move each white object that O references to the gray set. This ensures that neither this object nor any object it references can be garbage collected. Then, you move O to the black set, and then you repeat these steps again until the gray set is empty. When the gray set is empty, the scan is complete. The black objects are reachable from root, while the white objects are not and can be garbage collected. Since all objects not immediately reachable from the root are added to the white set, and objects can only move from white to gray and from gray to black, the algorithm preserves an important invariant. No black object references any white object, and this ensures that the white object can be freed once the gray set is empty. This is called tricolor invariant. The tricolor method has one important advantage. It can be performed on the fly without halting the system for significant periods of time. The system can perform garbage collection periodically rather than as needed, and the need to touch the entire working set on each cycle is avoided. The garbage collector may simply discard the unreachable objects and leave other parts of the system the way it is, and this type of garbage collector is known as a non-moving garbage collector. In other systems, the garbage collector might move some or all of the reachable objects into a new area of memory and update all references to the objects, and this is known as a moving garbage collector. Why the distinction? It seems on paper that the moving garbage collector may appear to be doing too much when compared to the non-moving garbage collector. However, the moving algorithm leads to several performance advantages both during the garbage collection phase and during the program execution. Some of them are: the space that was freed up when the garbage collector moved the reachable objects into a new memory is now considered free space without the system needing to do any extra work to provide this free space. In contrast, a non-moving garbage collector will need to ensure that it checks each memory occupied by each object and ensures that it is now free. This gives the garbage collector an ability to rapidly allocate new objects because the algorithm naturally creates large swabs of free memory. All the system needs to do is to increase a free memory pointer to get access to more memory. A non-moving algorithm will eventually lead to a fragmented heap, and this will in turn require very expensive requesting of the list of free available blocks of memory in order to allocate new objects. And finally, objects can be moved very close to the objects they refer in memory, increasing the chance that they will be located in the same cake line or virtual memory page. This can significantly speed up access to these objects through these references. However, it is not all rosy with moving systems because their implementation does not give much room for pointer arithmetics, and all references to objects are managed by the garbage collection environment. This is because any pointers to objects will be invalidated if the garbage collector moves those objects. And now we are done with that, let's look at reference counting. Reference counting is an alternative approach to automatic memory management where each object tracks how many references point to it. When references drop to 0, the object is immediately collected. The main advantage of the reference counting over tracing garbage collection is that objects are reclaimed as soon as they are no longer referenced, and this is done in an incremental fashion. In real-time applications or systems with limited memory, it is important to maintain responsiveness, and reference counting performance does not deteriorate as the total number of free space decreases. Reference counting has three main disadvantages over the tracing garbage collection. First, the frequent updates it involved are a source of inefficiency. Reference counting requires every memory managed object to reserve space for a reference count. In tracing garbage collectors, this information is stored implicitly in the references that refer to that object, saving space. Secondly, reference counting can't handle reference cycles, an object which refers directly or indirectly to itself. A mechanism relying purely on reference counts will never consider cyclic chains of objects for deletions, since their reference count is guaranteed to stay on 0. Methods for dealing with this issue exist, but can also increase the overhead and complexity of reference counting. In a concurrent setting, all updates of the reference counts and all pointer modifications must be atomic operations, which incur an additional cost. So let's look at some implementation strategies of reference counting garbage collectors, starting with weighted reference counting. In weighted reference counting, each reference is assigned a weight, and each object tracks not the number of references to it, but the total number of weights of the references referring to it. A newly created object has a large weight, say 1000, and whenever there's a new reference to that object, the weight of the original reference is split in two, and one half points to the new reference. Since the total weight does not change, the object reference count does not need to be updated. Destroying a reference reduces the total weight by the weight of that reference. When the total weight becomes 0, all references have been destroyed. Now, let's look at deferred or indirect reference counting. Deferred reference counting is an optimization for reference counting that minimizes its core weaknesses. By delaying the update of a reference count for certain objects, particularly those stored on the stack, instead of updating counts for every reference change, it postpones these updates until a designated reconciliation phase. These can significantly improve performance, especially in languages where stack references are common. However, some drawbacks of deferred reference counting are: 1. It requires compiler to support, identify, and track references, especially those stored in registers and on the stack. This strategy cannot reclaim objects with a cyclic reference where objects refer to each other in a loop, and it may require the stop word reconciliation phase, which can pause execution. So there you have it. That's going to be all for that on our lessons on garbage collectors today. Hope you found this useful and interesting. Absolutely smash that like button and ensure you subscribe to the channel so you can get access to all of our videos as they drop. Now, I did remember that I said I have a challenging question for you at the ending of this video, and I'm going to hit you with that question now. Can you tell me which type of implementation strategy is used for garbage collection in JavaScript?